Have you ever wondered how self-driving cars see lane lines, or how your phone's camera identifies objects? It all starts with edge detection. Finding edges is a fundamental step in computer vision. It drastically reduces the amount of data to process while preserving the crucial structural properties of an image. Today, we'll explore the most famous method, the Canny Edge Detector. What exactly is an edge? In a digital image, an edge is simply a region where the pixel intensity changes sharply. Mathematically, we can find these rapid changes by calculating the derivative of the image data. Where the intensity jumps abruptly across the pixels, the derivative hits a distinct peak. So, edge detection is essentially a mathematical search for high gradient areas. But there's a major catch. Real-world images are never perfect. They contain random pixel variations called noise. If we directly take the derivative of a noisy image, the noise gets mathematically amplified, creating false edges everywhere. To fix this, we must first smooth the image using a mathematical filter before we even start looking for gradients. The Canny algorithm begins with a Gaussian filter. We slide a small grid of numbers, called a kernel, over the image. This kernel calculates a weighted average of neighboring pixels, with the central pixel carrying the most weight. This convolution process blurs the image slightly, effectively melting away the high-frequency noise while keeping the true structural edges mostly intact. Once the image is smoothed, we apply gradient filters, typically the Sobel operators. These are small matrices designed to detect changes in specific directions. By convolving the image with a horizontal Sobel filter and a vertical Sobel filter, we extract the horizontal and vertical intensity gradients. These gradients tell us exactly where the image intensity is shifting. With the horizontal and vertical gradients calculated, we combine them to find the overall edge strength, or magnitude, using the Pythagorean theorem. We also calculate the gradient's direction, which points exactly perpendicular to the edge itself. Knowing both the strength and the direction is absolutely crucial for the next, more advanced stages of the Canny algorithm. Up to this point, we've essentially built a standard Sobel edge detector. The results are okay, but the edges produced are often thick and fuzzy. In 1986, computer scientist John Canny introduced 3 additional steps to transform these fuzzy boundaries into crisp, single-pixel-wide lines. Let's dive into these revolutionary steps that set Canny apart. The first enhancement is non-maximum suppression. The algorithm scans along the direction of the gradient and checks if the current pixel is the absolute maximum among its neighbors. If it's not the strongest point on that thick edge, it gets suppressed, meaning it's turned to black. This brilliantly thins out the blurry edges into precise, razor-sharp lines. Next is double thresholding. We set 2 limits, a high threshold and a low threshold. Any edge pixel with a gradient stronger than the high threshold is immediately classified as a strong, definite edge. Pixels below the low threshold are dismissed as irrelevant noise. Pixels falling in between are labeled as weak edges. This categorizes our edges but leaves us with a puzzle. How do we treat those weak edges? Canny solves this using edge tracking by hysteresis. The rule is simple. A weak edge is only kept if it is directly connected to a strong edge. It assumes that true edges are continuous, flowing lines. If a weak pixel is isolated, it's discarded as noise. This brilliantly connects broken edge segments. While Canny relies on first-order derivatives like Sobel, other methods do exist. The Laplacian filter, for example, uses second-order derivatives. Instead of looking for peaks in the gradient, the Laplacian looks for zero crossings, which are places where the second derivative changes sign. Though mathematically elegant, the Laplacian is highly sensitive to noise, which is why Canny remains the gold standard. To summarize, the Canny Edge Detector is a robust 5-step process: Gaussian blur, gradient calculation, non-maximum suppression, double thresholding, and hysteresis. By carefully filtering out noise and intelligently tracking lines, it extracts clean, precise boundaries from chaotic real-world images. Whether it's medical imaging or facial recognition, Understanding edge detection is your first crucial step into the incredible world of computer vision.